Hi, good morning again. Um, Today also we will introduce something related to gravitational potential energy. There are more, let's say, physical situations where we have something like lifting objects. Then what you're doing is your object may be here and you're gonna apply a force and you're gonna lift upward like this. Now this here is the case where lifting is different from carrying. And actually here the work done is FD, and the force and the displacement are in the same direction. Then if I will lift this object for a vertical distance h, this is going to be mg times h. M here, it is the mass in kilograms. G, it is acceleration due gravity, and that is 9.8. H here, it is the vertical distance, and this is in meters. Okay, and we call mgh, like I'm gonna use for it ug means gravitational potential energy. It depends, of course, on the mass, it depends on g, it depends on h. Okay, then mainly I will say in a certain case the mass is going to be the same, g is the same, then it will change with the vertical distance. Now, what I defined last time, it is 1/2 mv squared. And just here again, m, it is mass, and this is in kilograms. V, it is the speed in meters per second. Now, something that I will say worth saying here is when you double the mass, you double K. But if you double V, this is gonna make it 4 times of kinetic energy because it is squared. Now we can use a gravitational potential energy to simplify calculations. Okay, for example here, if I will sometimes maybe we are talking about going into steps like this, or going using, you don't have to deal with that complicated situation. What you need to do is just I'm worrying with that h is okay. Then I will say work done by gravity does not depend on the actual path. Like if you will take your object direct right away from here to here, or you took it over, as I said, stairs, but it's the same. Or if you do this using any method, then if your initial is the same in both cases and final is the same in both cases, then this is going to simplify your solutions. We can do here, define something called total mechanical energy. And that total mechanical energy, we use for it E, and it equals kinetic plus UG. Now, what I can do is here, I have two situations. We can use conservation of energy, of mechanical energy, to say, of course, EI equals E final. From early, let's say, physics classes or science classes, that energy cannot be destroyed, energy cannot be created. And this is like the fancy name for it, conservation of energy. Then now here, if you have Ki plus UGI should equal K final plus UG final. Their total should be the same. We can use sorry we can use this formula or this equation to calculate the speed of a roller coaster from its height. Then I can do that, and then I will say we have here a roller coaster that is looking like this. This is where my cart is initially, and this is the start. And here my VI equals 0. And let's assume that distance here is 25 meters. And here it is 20. And I will maybe also, I want to find what is my V here at the finish line or whatever, when I will end up. Sorry. Now, if I will compare here, okay, let me write for you first the question. The question is, what is the final speed of the roller coaster if it starts from rest okay, and here I will say we're gonna assume no frictional forces. Now, whenever we are going to do these, I will say energy conservations solutions, we need to consider I and final, your initial point and your final point. Now, initially, okay, I can say it started from zero, then no kinetic energy, but it has gravitational potential energy. Now, something that we need to know also whenever we are dealing with UG, we need to define a reference where my UG equals zero. To make my calculations simple, I will make that UG equals zero at this level here. And then I can apply EI equals E final. I like always to have a chart here, and let me show you what I will include in this chart. I'm gonna say I final. Okay, let me add another one here. I have only two energies here. Then I will say here, this is my I. And this is my final. For K in joules, for the initial, it was 0, and I need to find 1/2 mv final squared. Now for UG in joules, okay, if I look here, it is 20 meters above, then we're gonna say mgyi, and then when it reach here, it will be 0. I did use my level so that it will make it easier for me to get rid of some of the quantities. Here, you're gonna add the first row. Okay, we said EI equals E final. Then 0 plus mgyi should equals 1/2 m v final squared plus 0. Now here I can easily cancel the mass, but I want to bring to your attention that this is not the case with all the problems. Then don't make it a habit just to get rid of the mass, unless mass appears in all the what they are called the, I will say, the terms. Then here you will say v final squared should equal 2 times g times yi, and that is 2 times 9.8 times yi, which is 20, and then v final is gonna come to be 19.8 meters per second. Alright, then here I did use that easily to make like kind of conversions and stuff. Okay, that is really related to maybe speeds, accelerations, or whatever. Now we will say that this like gravitational potential energy it is related to a force that we call it a gravitational force. Now we will classify these forces into conservative and conservative forces. Then gravitational force, it is one of the conservative forces. Now, what is really the conservative forces? They are really, having some characteristics One of them is that they are really having conservative forces having a potential energy function like we did here, and it is stored energy, like we can store energy in these systems, and that energy, it is completely recoverable. We want these forces. These are good. Now, also for a conservative force, its work is independent okay, let me write this again. Independent of the path, which means it depends only on initial and final. All right, then these are really the characteristics of potential I will say conservative forces. Now, one thing that is really also here we need to add is potential energy means stored energy. There is another type of energy, we call it elastic potential energy. And this is the energy that we can store in springs. Now, based on Hooke's law, okay, we can actually, I will say, let's do this like simple here. If we have an experiment like this, we have like a mass here attached and we have a spring. Springs are really characterized by K, which we call it a spring constant. And it is in newtons per meter measured. Now, for any spring, if I will change the mass, I'm gonna give you like numbers, okay? Let's assume here I will be okay, just making numbers easy. 1, 2, 3. Let's assume I have a stiff spring, and I did add 1 kilogram here, 2, 3, 4, 5, and then I'm gonna measure how much is gonna stretch. Let's assume in meters. Let's say this is 2, then this one should be 4, this one should be 6, this one should be 8, should be 10. Of course, my numbers are not reasonable because usually the springs that we are using, they are not like this, but just because I want you to display the importance of, how numbers are really looking. And then here, if I will plot x in meters first versus the force in newtons, we are going to get a straight line. Now, Hooke's law that I was talking to you about before, F equals negative kx. This is the stretch or the compression in the spring. It should be in meters. Okay, then here x, it is either the compression or the stretch, and that is going to be in meters. Now, remember at the beginning I told you if I have a force that is not constant, then I will use the area under the curve. And when I will use the area under the curve, I will say, okay, this is the area of a triangle, and that is really here x, and that here it is kx as magnitude. Then I can say that the work done, it is 1/2, because this is a triangle, the base times the height, and this is gonna give me 1/2 kx squared. Then now here we can define also US, I will call it elastic potential energy, as 1/2 kx squared. And k, it is the spring constant. It is in newtons per meter. And x, it is the stretch in meters. We're gonna use so many of these springs in the problem solving later, when we will do, okay, we will do like kind of problem solving. Now, one of the things that I want you to know that is, now I can, every time I'm gonna add an energy, I will make conservation of energy more general, and then I will say EI equals E final, which means I will say KI plus UGI plus USI should equal K final plus UG final plus US final. Now, remember, this is kinetic. It is 1/2 mv squared. UG is gravitational potential energy, mgh. And finally, US, it is 1/2 kx squared. We call it elastic potential energy. Okay, I will stop here because I want to go to non-conservative forces and talk in general about conservation of energy and solve problems in the next, hopefully, video. Okay, thank you.